All right, this problem is going to be about solving the system differential equations with an application. And an application here is what we have here is we have two tanks. We have tank 1 with water in it with a initial concentration of C1 naught. We have a tank 2 with a concentration of C2 naught, and both have water. Tank 1 has water W1 in gallons, and tank 2 has water of W2 in gallons. And we have this water, tank 1, we have water transferring over to tank 2, and we have tank 2 transferring water over to this truck. It's not a pretty truck, but it's a truck. And this truck has to be able to hold both the amount in both tanks with a concentration of solution and the water, so it won't overfill. So that's kind of the picture of the problem. Now the thing here is initially we have water, a bunch of water, one's being transferred to the other. Now the worry here is tank 2, because tank 2 could overflow. So what rate can we prevent from tank 2 overflowing? That's just one question. And really modeling this system is going to take a couple of differential equations, and it could be a pretty good model. Not a great model, but a good model. So there's other physical considerations that could be thought of, but just try to make it simple. And really, we want to try to solve a, really answer some questions. Really read the description of the problem out and then solve the problem. So that will be on the next chart. But you see that there's concentration. When I said concentration of solution, it's in this case it's salt. All right, here's the interesting problem that I was going to talk about. It's better to read the situation out and instead of me just describing it. This helps. So tank 1 has a capacity of W1 gallons, connected to a tank 2 with capacity of W2 gallons. Tank 2 is connected to the tanker truck, and both tanks contain a dissolution of initial concentrations C1 naught and C1 0 and C2 0. And at time t equals 0, we start to transfer the solution from tank 1 to tank 2 at a ratio of R1 gallons per hour. That's a rate. And the solution from the tank 2 to tanker truck at a R2 gallons per hour. That is a second rate. The tanks have no lids, so it's possible for the solution to overflow, spill over. The tanker truck has a capacity bigger than W1 plus W2. Suppose both tanks are full at T0, and there's a continuous mixing in both tanks. So the salt is mixed in, so it's going, whatever is being transferred over to tank 2 from tank 1, the concentration of salt is going to increase over time. Okay, answering this question, you say, well, draw a picture and set up and label everything carefully. Now I started the picture, and so that's partially answered. Then it says given a condition on R1 and R2 to ensure that there is no spillage of the solution at any time. And C part is, at what time will a tank 1 be empty? How does your answer depend on R1 and R2? Assume R1 is less than R2. Find the C2 function describing the concentration of tank in tank 2 at a given time. Find the concentration of the solution in the tank 2 at a time when the tank runs out of the solution. So here's where the questions hopefully we can answer. I may not answer all of these but I will give you direction on how to answer it. So let's look. All right, to represent what is described in the earlier chart, the first chart. First of all, let me look at the initial condition here. Now we talked about we mentioned in the problem that there was an initial concentration. The initial concentration of the salt to water ratio is S1 over W1. Same thing with tank 2, S2 over W2. Now to describe this whole system, it's described in a coupled equation, because there's a coupling because we have something coming into to the tank 2 with a rate 1 and a concentration 1. That is going to change over time. The rate's going to stay the same, but the concentration over time coming from the first tank is going to change over time. Now initially in the first equation we have a C. C is it can be anything on the outside of the world coming in on the first tank because it initially starts with S1 over W1. But there is versus that something going out, which is S1 over W1. Typically this what models that rate of change and transfer of tanks is what's coming in and what's going out. And the coupling is what's coming in and what's going out. So this is a coupled first order differential equation that has to be solved. We have initial conditions here. C1 at T0 is equal to S1 over W1. C2 at T equal to 0 is S2 over W2. So that is your model, basic model of modeling this system. Okay. We did lay out the design of the whole thing. But now, and you see that in the lower corner here, just a reminder of the picture, and it's a couple of equations. Now, given a condition on R1 and R2 to ensure there's a spillage of solution at any time, what condition that you need to have? Well, you need R2 to be greater than R1, which makes sense, because if R1 is greater than R2, there is a chance that that you could have a spillage in tank 2. So you need R2 to be greater than R1, or R2 to go out faster than R1 to not have spillage. So that pretty much answers that. That really answers the mail. Okay, here we have another, let's see, C part. It says, at what time will the tank be empty? How does your answer depend on R1 and R2? So we have our coupled equations. We have our initial conditions. So what time will tank 1 run out? Well, that really basically means that when does tank 1 go to 0? How long will it take with tank 1 to go to 0? All right. So what we need to do is if we just look at the first equation, it's not really coupled to the second equation as much as the second equation is coupled to the first, because there's no C2 here. There are cases when there's a full coupling of the two equations to each other, But this C1 here is a constant. You have C1 is the concentration 1 is not only has constant, but it also is only related to C1. No C2 in here. So this is a differential equation that can be you can find the solution to. Now, if you look at you can lose all kinds of differential equation techniques. I didn't point anything out here. I could just probably eye it, and I can look and see that the general solution is here. That's the general solution. It's right here. This is the general solution to the equation. So if I substitute this into this equation, I will get this. This would be some constant p, because this is just a constant p. So if you just test that out, you'll see that that is the solution. Now we have to include the initial conditions. We have to apply initial conditions because we only have a general solution, and that's what I do here. So really, the interpretation that means is, when does the concentration in tank 1 go to 0? But going back, we have to apply the initial condition first. Is that what we have here? When we apply that here and we set this equal to S1 over W1, we get this solution here. So this is the solution applying with the initial condition. Well, we need to set this in equal to 0, and we need to solve for t. What time does this concentration go to 0? So we need to find t. And when we do that, I didn't go through all the algebra for this, but may have to check me on this, but I'm showing you the steps and the solving this, and that's just how you solve for t. So you're going to get some exponentials. You're going to get some stuff on the that you're going to have to take the log of both sides to get to t. And I'm not going to include that here, but that's something that just needs to be mentioned here. Okay, so that answers the C part. What time? And so how does your answer depend on R1 and R2? Well, it looks like it just depends on R1 and doesn't depend on R2. I don't see anything in R2 here. Okay, so D part, if assuming R1 is less than R2. Now, remember that we mentioned that in order to avoid spillage, that R1 had to be less than R2. R1 had to be less than R2 to avoid spillage. Okay, so find the function C2. Find the function C2. Describing the concentration of dye in tank 2 at a given time. But what does that mean? Now it says assume that R1 is less than R2. So if we did the other, just to mention here, because I am not going into it, but if R2 is greater than R1, that may change how we solve this system. That may change things. That may be some more complications to the model. There may be some things to consider. I don't know. I hadn't looked at it, but that they put that there to say assume that. But anyway, that goes back to part B, because that's a condition of avoid spillage. So what D is really saying here is you need to solve, what you want to do is solve the differential equation for concentration C2. That's the only thing it's asking. The only difference, caveat here, is that you're going to have to include the solution to C1 into C2 because it's a coupled equation. It's C2 is coupled to C1. So you substitute that in there. Now you solve just like the C1 concentration, you solve a inhomogeneous differential equation. This time, this inhomogeneous differential equation will be in C2, only C2, once you substitute in for C1. Your rate R1 is a constant. It's not dependent on time, it's just a constant. R2 is constant. Doesn't depend on time, it's just a rate. If it was dependent on time, this would be more complicated problem. Now, C2 is dependent on time. It is dependent on time. It's the dependent variable on time, which is T is the independent variable. So, if you substitute that in, what do we do here? What do we do here? Okay, we substitute that into C2. You see the general solution with the initial condition included with a constant for P. And we substitute that into the equation, which is a inhomogeneous first order differential equation. And we have the equation for C2 here. This here. That's your equation. Now what we need to do is we need to solve that equation using certain methods. There are methods in differential equations in DE that we can use. One we use is including an integrating factor. Since we know that our first guess that anybody's first guess as far as differential equation, you want to try the exponential. And you can sit there and see to look at the exponential, and that's the only way you can match up that derivative on the left side of the equation for C2 concentration. So this integrating factor is what you use here. And substitute in and see what you get. Alright. And substituting that in, you use that integrating factor, but here, this left side is just the derivative of the product rule. If you take the derivative of the product rule of C2T and the exponential here, you will get the left side of this equation going back up here. You'll get that up here. This right here. This is the product root of this. Now you got a d out here, but it's a d over dt, but that dt is taken on the other side. Is integration by separation, which you have here. And you take, I didn't include the integral here, but you take the integral of this. There should be an integral here. An integral here. So you integrate this, it's just like taking the integral of dx, which is x. Here on this side, this is where you integrate here. You integrate this side. And you got, and t is, you see the exponential is a function of t. Once you deal with these constants, this integral is pretty straightforward. It's just 1 over e to the t or e to the at is, integral is 1 over a e to the at or something like that. Something like that. Simple integral. So once you get that, you can solve both sides. You can divide that exponential out and solve for CT. So that's what I did here in the next. Now C2 is the general solution to the equation, partially general, because this infused into the solution is the solution to concentration C1. So it's partially general, partially particular. So we need to apply the initial condition to C2 concentration to make it a particular solution. And that's the initial condition that we need to satisfy. But by the way, subscribe to my channel, Alpha Mad Scientist. Like, share. I'm hoping this helps somebody. Just want to say that before I forget. Okay. Now, we apply that initial condition. It probably makes the solution. This is a long solution, so it's going to really make it even more long-winded. So you'll see this in the next chart, which I didn't include the. I really didn't include the whole thing written out. I just put a P naught in there, and you see here where what P naught is right here. Now, there's no guarantees. I could have made a mistake, typo, error, whatever it is. That's why I said it is your duty to go back and check my work, because I may have made a mistake. And these things easily happen. So trust but verify. But I have given you what you need, giving you the solution and the layout of this type of problem, because there are other type problems that are like this. Now the other thing is the last part is, which I didn't do. I think you can easily do because we did it for concentration 1. Is when does the concentration of in the tank 2 disappear? Well, after applying the initial conditions for C2, all you need to do is make C2 equal to 0 and solve for T. One thing I hadn't tried is the maybe taking the limit of C2. I've seen that tried before too, taking the limit of C2 as it approaches 0. What do you get? That may be a possibility. I don't know. I've seen that in other problems. But anyway, I didn't do that. I think it's something you can do. It's just a lot of algebra. If I decide to, I may have something written out on my Patreon channel that I'm hoping to put more detailed information up and maybe get some subscriptions for that information. But if there's anything more detail is going to be added, it's going to be in my Patreon channel. So anyway, share, like, subscribe. I really hope this helps somebody. This is a problem that I actually tutored somebody on, and we went through, and it's long-winded, but this is what this math is all about. It's applying it to real physical problems. Just coming up with the initial values and general solutions and initial conditions. Really, sometimes you're like, why am I doing this? Well, this is a reason to show why you're doing this. You're applying this to something that is somewhat almost a real world problem that people encounter every day. So, hope this helps.